stand by. Good day, everyone, and welcome to IMAP's corporate webinar, High Reliability Component Attachment Process for Less than 5 Micrometers Placement Accuracy, sponsored by Palomar Technologies Incorporated conference call. This web seminar is being recorded. This web seminar will consist of 50 minutes of lecture followed by a 10-minute question and answer period. At this time, I would like to turn the meeting over to Donald J. Beck, General Manager, Palomar Technologies Assembly Services. Donald Beck has led the Assembly Services Division at Palomar Technologies for the last 5 years, expanding it from a tiger team to a major player in precision microelectronic contract assembly. Under Mr. Beck's tenure, Assembly Services has grown 300% and continues to develop new processes and solutions for customers worldwide. Mr. Beck, please go ahead, sir.
Thank you, and good morning. I'll start by acknowledging the fact that this paper was written with the collaboration of Ziegler Bach, who's Senior Application Engineer at Palomar, along with Dan Martinez. So at Palomar, one of the key areas that draws potential customers would be our high accuracy products and offerings, specifically better than 5 micron placement processes and procedures. So I will attempt to step through. It looks like I've lost a little bit of the connection here, so I'm waiting for it to step through. So Lori, right now it looks like I'm paused and it's trying to reconnect, which I'm in the process of trying to get back in right now. I apologize for this. So it looks like at this point I'm paused at the first screen, and we'll try to reconnect as quickly as I can.
And sir, I can move the slides for you if you'd like.
Yeah, why don't we go ahead and try that, because I'm not moving it. So if we can go ahead and go to the agenda slide. Yeah. And again, I'm not seeing anything but the first screen on my side.
And we are displaying the agenda items at this time, sir.
Okay. Well, I don't see that. Let me try this here. I guess the other way I could do it is to play along separately, because it's not connecting me back in at this point.
And Brian has joined us also, so he might be able to help move the slides.
Hey Don, this is Brian from IMAPS, of course. I'm seeing everything fine, so I'm wondering if maybe your connection has dropped. I was able to advance the slides as well, and we do see the agenda on. Maybe if you drop you close your webinar window altogether and try to reconnect from that email I sent.
Right, right.
I'm wondering if maybe you just had a quick blip on your end where you lost the connection and it's just locked up.
Yeah, I will try to do that.
And if that doesn't work, what I would suggest, if you could pull the slides, separately from your desktop from PowerPoint, Lori or I will step through the slides so that we match exactly where you are,
right.
and we'll control everything for you in the live environment.
Right. Yeah, I'm trying to reconnect right now, so it'll take me back to the beginning, but I should be able to start to join right now. And at the same time, I'll go ahead and... Okay. So it looks like I am back online now. All right, and I'm moving.
Okay, I see the agenda, so it looks like we're all set.
Okay, sorry.
Sorry about that, Don.
Yep. So I'll step through the agenda, and again, apologize for the delay. We will go through the key objectives, material considerations, talking about drawing requirements and those material issues that are particular to high accuracy. The process and process certification, the types of standards that we've developed to help ensure that equipment is meeting minimum requirements to support those high accuracy processes. Tooling, the different types of tooling that we have designed and tested to support processes, and measurement capabilities for measuring different types of high accuracy requirements in both top-down and edge views. We will then go into 3 different case studies where I'll present results of different applications that targeted either 5 micron or better than 5 micron, in some cases 1 to 2 micron requirements for customers that Palomar supported. Then we can go into questions and wrap up. So the key objectives, the main objective of the presentation is to share our experiences associated with high accuracy placement. Palomar, we believe there are fundamental factors that must be managed to support these types of processes. That is the equipment, the performance, specifications, the environment, the materials, drawings, verification, tooling, the type of tooling that's designed for the type of part you're trying to process, and the measurement techniques. The material overview will go through the drawing requirements, part tolerances, the types of fiducials that we know work well, along with those that we know will have issues. Edge alignment features, again, that's looking at the difference between top-down and edge alignment features for, say, laser-type products. Component presentations, talk about waffle pack and gel pack. So for material considerations, the material, of course, has to be dimensionally stable. The planarity, size, and tolerances have to be very well defined. The fiducials have to be very crisp, repeatable, and unique. We have to have a consistent material quality, cleanliness. Pre-qualified vendors really help that to ensure that you have a good product coming in. And then a clearly defined alignment and measurement strategy to validate the materials going into those processes. For drawing requirements, a lot of these are all pretty well-known standards. You know, CAD, ASME types of standards and equipment used for, or systems used for designing. The ones that are of particular attention to pay to would be for the normal distributions based on, the high assembly tolerances that are typically based on normal distributions. And then the call-outs for the tolerance, perpendicularity, and parallelism and flatness. All right, there we go. So for the chip-on-substrate standards, some of the tolerances that are shown here, for example, the front face overhang, we will spec that down to as low as 1 micron and show that depicted on the drawing for perpendicularity and flatness as shown here, and then the parallelism or smile across that part type. Fiducials are, of course, very important. There are differences between thin film, of course, and thick film fiducials. So we find for better than 5 micron requirements, you really have to have a thin film type of fiducial to start with. Thick film is really hard to manage, specifically when you're looking at high temp co-fire, low temp co-fire, or a thick film product. So lithography is what we know works. Types of fiducials that work well would be this square type of feature. Of course, standard cross is always good, but any unique feature will work as long as it's consistent from part to part. There are other fiducials that are not suitable for high accuracy. The protruding edge here, where you have quite a bit of difference or variation between top and bottom surfaces, scratched or abraded surfaces, and just generally edge. When you're looking at edge product, of course, at high magnification, edges tend to look different from part to part. Other notes that better clarify the assembly requirements would be the temperature limitations for the epoxy cure and solder reflow, surface roughness, the metallization scheme, whether it's the metal deposition, the applicable solder thickness and tolerance for that, plating and such, surface quality for burrs, peeling, and metallization, the handling requirements for EST sensitivity, mill standard or any types of JEDEC standards, no touch zones for the part type. That's a big impact for the die collet, and if there are sensitive parts, the bond force that's allowed. And then for the bond thickness requirements, depending on the part type that you're trying to put down. Component presentation. There are, several types of presentation package that would consist of, say, gel pack or waffle pack. We find both work very well for these high accuracy processes. The gel pack offers some superior protection for shifting because the parts won't move at all during that shipping or presentation process. But the waffle packs, of course, allow for a faster dwell time or cycle time due to the fact that there is no dwell time needed to pull out of the gel. The gel pack is the common issue for the component supplier. They want to ship, with a high tack level to verify that the components don't move during shipment, but then the user tends to have a hard time picking out of those very high tack type of products. So it's really important to get the right gel pack for the component that you're wanting to process in the line. And then, of course, for waffle packs, they have a very simple calculation guide online that will basically design that waffle pack for you. Going into high accuracy processes, our assembly strategy is to validate the materials at incoming inspection. We also will verify equipment is performing within minimum guidelines at least once per 24-hour period. We will then perform in-process inspections to make sure that the process doesn't drift, and offline inspections based on A2L sample type of inspection. You need to decide up front, of course, how much to invest into these processes, because it does take time from building real product, determine how efficiently the processes can be performed, to try to get through that as quickly as, but as important, repeatably as possible. A couple of the different process options that we'll talk about are for both epoxy and eutectic die attach. The solder reflow, we use for the high accuracy processes a specific type of reflow tool, pulse heat stage. We refer to this as a silver bullet. It was designed specifically to manage the growth of the heater bar to minimum standards. So everything is designed to lessen the impact and CTE mismatch between the part and the heater bar itself. And then we use our patented high temperature control process that allows us to control that process to within 1 degree C from process to process or profile to profile. Another option is where the silver bullet obviously will heat through the bottom of the part using conduction. We can also heat through the top of the part using a heated tool, which is shown here. So in this option, we're just taking that technology, reversing it, and putting the heater bar into the bond head itself, and with a tungsten carbide tool that's bonded directly into the ceramic, heating through the component to reflow the solder between the wafer or substrate and the die. For our reflow profile, we use a computerized PID. We can maintain that to within 1 degree C from profile to profile, ramp that up to as high as 450 degrees C, and specifically define the dwell times, the cool down, the ramp up. Those rates are all programmed in. For epoxy attach, there are several ways and methods to deposit or transfer the epoxy. For high assembly or throughput applications, the offline dispensers are the best option. However, for some applications, we find that specifically for smaller components, such as the VCSELs or PIN diodes that are shown here, on the order of 290 or less than 300 microns, it's very, very hard to get the consistent volume of solder deposited through, say, an auger pump. And in those applications, we might use a dot pot with a pin dot transfer to get that epoxy transferred for each of the components. For our vision, all of these are important. The vision system needs to resolve the difference down to 1 micron. Should be 256 grayscale. Autofocus routines. Any variation in height will have a critical impact on the component placement. So autofocus really helps to manage that. And the ability to import previously stored models. A lot of these are standards with any type of Cognex system. That's the system we use, or any other vision systems that are out there. We find the use of synthetic models are very helpful in the ability to mask out areas that may introduce variability into the process. For synthetic modeling, this allows you to create a perfect fiducial, to model the exact type of fiducial that you're looking for, and to mask out features that aren't important or that would hinder the ability to find that consistently. So you can see here this synthetic cross that we've modeled to emulate the actual feature on the part, or edge as shown here, or even special or unique features that I'm showing down here. Also, when we're looking at edge alignment, for, say, laser type of product, what we have the ability to do is to look at as many as 3 different points or fiducials to, for example, look at the upper left and lower left to set, say, that Y dimension, and then come back and find the edge of the component to set the Y dimension. So again, you can set your X tolerance by looking straight down at the front, upper left, lower right, and then come back and find the edge using those 3 fiducials. And if you can see everything in the same screen, there's no need to actually even move the camera. You can pick all of that up in that same view. For the measurement of the product, the measurement capability, we'll discuss the metrology correlation, edge measurement systems, the auto measurement of and assembly equipment, P-side down measurement for laser product, gauge capability, which is a needed requirement for the high accuracy product, or I should say measurement systems. For looking at the product in X, Y, or Z, there's the Nikon systems work well. This allows you to use up to 5 different magnifications and to automate the step and repeat process for automated inspection routines. Now, when you're looking at edge product, that's where you have some challenges with laser systems looking straight down, and a system such as the Keyence will allow you to set the axis on the edge and give you a very accurate measurement of the difference between the substrate and the edge of the part. And taking it further, we've developed standards that allow us to inspect real-time on the die-attached system. So once that part's placed, we have post-placement accuracy check we refer to as PPAC that will go back and find where we put that part relative to where we expected that part to go. And taking that even further, we'll introduce what we call post-pick, which will take the image of the part before we put down and then translate that to features on the top surface of the component so we can tell you where we put that bottom edge of the part, which of course would be invisible after it's put down. That's shown a little bit better here. The correlation routine that we use is basically, again, looking at features on the bottom side of the part and transferring them onto the top of the part so we can then tell you exactly where the edge of that part was relative to the P-side down feature that we were intending to use. Now I'll transition to a couple of different case studies. So these are real products that Palomar has been supporting and building throughout the years that we've been doing this. The first one is an FPA die attach. This is a over 4.5-inch aluminum nitride substrate. It has over 900 passive components, 0102s and 0402s, 92 8mm die, and over 6,500 wire bonds. The requirement is that we maintain 5 microns in X and Y precision, and then a 3 to 5 micron adhesive bond line, which of course is very challenging. Finding the right viscosity adhesive is extremely important, and the process to support that. We've been building this product since 2009. We have all of the passive components are attached using our 3800 die bonder, and all of the FPAs are attached using the 6500 system. And at 6500, we have applications known today documented to better than 2 microns, even as low as 1.5 micron precision. So this is the product that we're referring to, again, the 92 CMOS die across the top surface. And in the real application, we'll show it here. The video is downloading now, and if anybody has any problems seeing it, please feel free to contact Brian, who can get that set up for you. Shown here is the 6500 system, where we're picking the die, the 8mm die, off of the gel pack and placing it onto that aluminum nitride substrate. We do that by transferring pin dot transfer 5 epoxy dots onto the aluminum nitride surface, and then going over and picking the 8mm die from the gel pack. And we will then hold that for a period of time to cure it, and repeat that process over and over for each of the part types or the components, all 92 positions. The second case study is for an optical cable assembly. And in this example, it was a startup company that couldn't afford the equipment right off the bat, so they teamed up with Palomar to help develop the processes and introduce that product into market. In this application, there were 290 micron lasers attached P-side down using gold tin. The requirement was better than 2.5 micron precision. Also required 2 other components, which were the lens and mirror, to be attached with optical epoxy. All of the parts were assembled on a 6-inch wafer with over 3,000 lasers or parts per 150 millimeter wafer. We've been building that product for 2 years. At this point, this customer has since bought their own equipment through Palomar and is building this product today. The customer is, again, since then, they've purchased the 6500 die bonder system to support the laser bonding, the 3800 for the lens and mirror attached, which was used here at Palomar. And again, that was successfully completed over several years. And in this example, we are reflowing the solder using the heated tool, pick and placing 290 micron die, and then going through the ramp and reflow process through the ceramic heater bar tool located directly on the bond head itself. Okay, just stepping back in. And again, if anybody has any issues seeing that video, please feel free to contact Brian after the presentation. The third case study is for a flip chip application, RFID. This was one that we were pretty excited about because it gave us an opportunity to look at anisotropic material, in this case ACP or anisotropic paste. The application required that we place 450 micron RFID components, ball bond presented to the 3800, already pre-flipped, that we were then flip chip attaching them onto a PCB, Of course, one of the byproducts with an ATP material is that you dispense that epoxy or pin dot transfer, place the part, and then snap cure. So you get electrical conductivity in the Z-axis only between that ball bump and the pad, but then it's isolated around it. So you basically are getting an underfill as a byproduct of that process itself. There's shown in the lower right is the actual product we were assembling. Again, we were using a thermoset anisotropic conductive material. The die were pre-flipped going into the 3800. Although we could flip them as part of that process, it would just take an extra step to do that. And I will step through the video now. And it should be, we're currently downloading the content for the videos. It'll come up and you'll see that we will do the pin dot transfer of the adhesive going in. That's our 3800 platform. The epoxy is in the trough, the presentation stage, pin dot transfer to the PCB. The area that you see that tooling is a heated stage where we're located now. The part is preheated to 110 degrees C. We pin dot transfer the epoxy, go and pick the part, and hold it for 10 seconds to snap cure it in place. And again, that's done 92 times throughout the whole part. The tooling that we have was specifically designed to support that part so that it doesn't move during the assembly process. So those were the three case studies that we showed that, again, were proven product that we've been building for customers, in some cases in excess of 3 to 4 years. And for new customers coming to Palomar, I think that's one of the main drivers is looking for high accuracy support, again, down to 2-micron precision. So at this point, I'd be happy to move into the questions and answer any questions anyone might have.
And thank you, sir. To our audience today, if you would like to ask a question, please press *1 on your touch-tone telephone. Just a reminder, if you're joining us via speakerphone today, make sure that your mute function is turned off to allow the signal to reach our equipment. Once again, ladies and gentlemen, *1 for your questions at this time. And a voice prompt on your phone will indicate when your line is open. Please state your name before posing your question. Once again, ladies and gentlemen, *1, and we'll pause for a moment. And I have no questions at this time, but once again, ladies and gentlemen, *1 if you have a question. And we do have a question. Caller, please go ahead.
Hi, Sean Sarbacher. I was wondering how you characterize and include thermal shifts and drifts of the placement into your placement precision results, how long you typically run the tests, how many samples, that sort of thing.
Yeah. Hi, Sean. We do that through DAC targeting. It's a great question, and of course, a big part of that high accuracy process. You really have to know where both the part and the bond head is throughout the entire process and duration of the product. We do that by calibrating known targets within the bond head to compensate for changes in temperature in the room and the environment, And of course, for the part itself, we do that through pattern recognition. One of the issues that you'd have that might be different between a standard product is for high accuracy, can't afford to have long pauses or dwells between the time that you're pick and placing. So if, for example, you're going through a training period or you stop that process, you'd have to back up in some cases so that you can recalibrate where both the bond head and the part is prior to pick and place.
Great. So how long do you typically characterize your runs in terms of your placement 3 sigma values, or is that typically a short run number with some maximum drift requirement?
Well, yeah, we do a DAC verification prior to each pick and place step, and it's done, you know, within milliseconds. So it's just part of the process. So I would say, you know, the sample time is every time you pick and place a part.
Okay, thanks.
And just a final reminder to the audience, if you do have a question, please press star 1 at this time. And sir, it appears we have no further questions. I'd like to turn the program back over to you for any additional or concluding remarks.
Great. Thank you. No, I just wanted to thank everyone who's listened this morning, and Lori for monitoring, and Brian for setting this up for me.
Once again, thank you for joining us. That does conclude our conference for today.